Energy Study Guide. Question 1. Fill in the blank with heat, thermal energy, temperature, and thermal equilibrium. Blank is the measure of average kinetic energy of the molecules in a substance and has units like degrees Celsius or Kelvin. This is the fancy science definition for temperature. You all know what temperature is, but now you need to know temperature refers to the average kinetic energy, or about how fast are the molecules in a substance moving, and we measure that with degrees Celsius or degrees or Kelvin. The total kinetic energy of all the molecules in a substance, so the mass and the speed of the molecules, is called thermal energy. Okay, so it's important to note all of these words, they kind of sound like they mean the same thing, but they're not. Temperature is average kinetic energy, or the measure of how fast the molecules are moving. Total kinetic energy refers to thermal energy. Blank is the transfer of energy from hot to cold, and it has three forms: conduction, convection, radiation. This is what we call heat in science. Heat is not, this is hot and this is cold. No. Heat refers to the transfer of energy. Okay? Blank occurs when two touching substances reach the same temperature. Keyword here is same temperature. The last word that we have here is thermal equilibrium. In the word equilibrium, you kind of see the word equals. Okay, that means the same. So thermal equilibrium is when two things are touching and they eventually become the same temperature or close to the same temperature. Container A has 5,000 milliliters of 60 degrees Celsius, and container B has less, 100 milliliters, but it's a little hotter, 80 degrees Celsius water. Which has more average kinetic energy? Why? Remember, average kinetic energy, anytime you hear that, you need to think temperature. So which one has more average kinetic energy? This one at 60 degrees Celsius or this one at 80 degrees Celsius? The answer is container B, because average kinetic energy means temperature. Perfect. Now, which one has more thermal energy? Why? So remember, thermal energy refers to the total kinetic energy of the molecules in a substance. So how much of it's there and how hot it is. The mass of the substance and how fast the molecules are moving depending on how hot or colder they are. Container A has way more mass, and even though it's slightly cooler, container A is going to have more thermal energy because it has way more mass. So container A has more thermal energy because of, we'll say, higher volume. Okay, there's more stuff. Okay, kind of like that video where the bucket of water had more thermal energy than that little teacup of water. Okay, write conduction, convection, or radiation under each example. Burning your hand on a pan's handle, that is physical contact. So anytime we see physical contact, that is conduction, or transferring heat through physical direct touch. Broiling a steak. Okay, I don't know if you know this, but if you have an oven And inside your oven, there are these, kind of like these wires, and if you turn them on, they get really, really hot. And so they start to make the food over here, and in this case we have a little steak. They start to make it extra crisp. That's why we like using a broiler. So the heat traveling from these rods that get really hot is an example of radiation. Okay, because these metal prongs are getting really hot and it's traveling through space onto the steak. A hot air balloon. Look at this picture. This is how a hot air balloon works. They put a flame here. They heat up the air inside, so hot air will be rising, and then cool air around it helps it sink to the ground, so they can alter the flame to make it go up, to make it go down, make it go left and right. So anytime you see hot air rising and cool air falling, we call that convection. Okay, convection. Microwave is using energy traveling through space, a transverse wave. So this is going to be radiation. Cool air falling, just like this one, anytime you have hot air rising, cool air falling, we're going to call that convection. Alright. Okay, a metal spoon getting hot inside of coffee. So if I have a coffee cup and a metal spoon, that's physical contact. So this is going to be an example of conduction. Being warmed by the campfire. So ignore my ugly drawing, but if I have a campfire and I'm over here, the heat is traveling through space and warming me up. This is an example of radiation. Frying an egg, again, this is my frying pan, this is my egg, the fire is over here. This is physical contact. So this is conduction. If it helps you on the test to draw these out, do it. Takes place in fluids. Okay, fluids can be two things. Obviously they can be liquids, but they can also be gases. Okay, so this goes to this over here, hot air rising, that's a fluid movement, and cold air falling. So anytime you see the word fluid, I want you to think convection. Number 4. Explain what will happen to a cup of tea and a cold soda if they sit in the same room overnight. So, I mean, you can do this at home, but I think you can kind of figure it out. They will both eventually reach what we call room temperature. Okay. So they're going to be at the same temperature. Okay, what is a thermoinsulator and what is a thermoconductor? And give an example of each. Okay, you need to know an insulator prevents the transfer of heat. So an insulator prevents heat transfer. So what are some things that do not let heat travel through it? That's called an insulator. Examples, remember that lab we did with the different sticks and you try to touch it to see if the heat traveled up the stick? We saw that wood is a good insulator, plastic is a good insulator. Okay, and why are your jackets, like those North Face ones, why are they so puffy? It's because air is a good insulator. It traps the body heat and it just makes you, or keeps you warm. So we can say air is also a good insulator. Conductors do the opposite thing. A thermal conductor lets heat transfer through it. Okay, provide an example. You should know by now the best conductors are metals. So if I'm using a spoon inside of my big pot of hot soup, a metal spoon is going to heat up because it's a conductor, but a wooden spoon is not going to burn me because it's an insulator. Okay? A metal object that measures 100 degrees Celsius falls into a bucket of water at 10 degrees Celsius. Explain how the temperature will change in the system. So let's draw a picture. So we have a metal object. Okay, this is 100 degrees Celsius. Okay, and then it falls into a bucket of water, and this water is 10 degrees Celsius. And it's asking you to explain what will happen to the temperature in this system. So let's go back to one of these definitions. Thermal equilibrium occurs when two touching substances reach the same temperature. So, you guessed it, what's going to happen when I put this hot metal into this bucket of cool water? Eventually, thermal equilibrium will be reached because these two are going to be touching each other. And so this one's going to get colder and this one's going to get a little warmer, and eventually thermal equilibrium will be reached. Okay? Eventually thermal equilibrium will be reached. They will have on or near the close of a temperature. So maybe this will go towards 30 degrees, and this will cool down towards 30 degrees, something maybe eventually towards room temperature, right? What happens to the motion of molecules when temperature increases and decreases? So, let's answer that question first before we draw the line on the graph. So, when temperature increases, you need to know molecules move faster and farther apart. We saw that with that one online simulation. And then the opposite is true for when the temperature decreases. Instead of move faster, the molecules move slower and come closer together. Okay. When molecules come close together, we call this they're condensing. You kind of need to know what that is for the SOL, but that's what it means. When you have two molecules and they're just coming close, the temperature is decreasing and decreasing, and then they eventually come together closer. That's called condensing. Okay, it says draw a line to show this relationship. So, speed of moving particles is on my x-axis. Temperature is on my y. I notice on my y I'm going cooler to fast to hotter. So I'm increasing the temperature. And here I'm going faster. So my line is going to look like this. As I'm growing, as the molecules are moving faster, it's because they're getting hotter. If something is slow, that means it's cool. If the molecules are moving faster, that means they're hotter. So you need to understand this relationship between the speed of molecules and temperature. Okay, we have three ways to express average kinetic energy or temperature. You guys all know the Fahrenheit scale. Okay, but we don't use that in science world. Those are not the SI units. We use Celsius, degrees Celsius, and we also use this other scale called K for Kelvin. There's no little degree sign for Kelvin. Right, and you have different things going on. Absolute zero, water freezes, water boils. What is 0K called, and what is this in degrees Celsius? So 0K You need to know it's called absolute zero. And it says, what is this in Celsius? So 0 degrees Kelvin, or 0 Kelvin, is equal to negative 273 degrees Celsius. And if your mind works in Fahrenheit like Mr. Otekin does, negative 460 almost degrees Fahrenheit. That's super cold. So it equals, let's just write the Celsius real quick, negative 273 degrees Celsius. What happens at this temperature? So we already know that when things get colder, they move slower and closer together. Absolute zero is when all molecular motion stops. So nothing's moving. So what happens at this temperature? All molecular motion, the motion of the molecules, are they going really, really fast, or are they getting slower and slower coming together? All molecular motion stops. It's like super epic Frozen. Okay. What happens to water at 100 degrees Celsius? So let's go to 100 degrees Celsius. What happens? Water boils. So we'll call this boiling point of water, H2O. Can the temperature of water increase to 110 degrees Celsius? So you might have done that lab where you realized once water starts boiling and it reaches 100 degrees Celsius, it never gets hotter. Boiling point of water means at 100 degrees Celsius, that's when it begins to boil, and water cannot get any hotter than this until it basically turns into a gas, and then you're just measuring the temperature of these surroundings. So no, it can't increase to 110. The planet Neptune has a temperature of negative 200 degrees Celsius, and Uranus has a reading of 190 degrees Celsius. Which planet is closer to absolute zero? Explain. So it's giving us the readings in Celsius, so we need to use this middle scale. If this is 0, remember math class, we're going down the number line, so this would be, you know, negative 10 degrees, 20 degrees, 30 degrees, and we need to go all the way down here to negative 273, which is absolute zero. So it says Neptune is negative 200 degrees. So if this is 273, let's just call this over here negative 200 degrees Celsius. And Uranus is 190. So it's going to be a little bit over here. Or excuse me, negative 190 degrees Celsius. So if this is Uranus and this is Neptune, it's asking you which one is closer to absolute zero. Explain. You're going to say Neptune because it's closer to negative 273 degrees Celsius, which is equal to absolute zero or 0 Kelvin. Neptune because it's closer to negative 273 degrees Celsius or 0 K or absolute zero. So all of these mean the same thing. This temperature, and this one. Alright, let's see the back. Phase changes. What must happen to change water vapor, a gas, so this is going to be a gas, to water, which is a liquid. Okay, so remember the phase change graph when you have, let's say this is a bucket of water. It's asking you how do you go from water vapor, this is the gas, how do you go from this to a liquid? Okay, this is very similar to what happens when we make clouds. Okay, So, in order to go from a gas to a liquid, you need to think, am I adding thermal energy or am I removing thermal energy? The answer to this is you are removing thermal energy. So, what must happen to change water, vapor, to water, a liquid? Thermal energy is removed, which means, am I cooling it or am I heating it up? I'm cooling it. Thermal energy is removed, cooling the molecules, which brings them close together, those gas molecules, which brings them together. And this is what we were talking about, condensation. So when these gas bubbles get colder, they're going to come more together, they're going to condense, and they're eventually going to make a liquid. So thermal energy is removed, cooling the molecules, which brings them together / condenses. Condenses into water, which is a liquid. Label this graph with solid, liquid, gas, melting and vaporizing. Okay, so you need to know this is time, so time is going. This is temperature, so I'm increasing the temperature. Time is passing. So I'm starting with a solid. As time passes, temperature increases, it plateaus. What is it doing here? Whenever it plateaus, whenever it's flat, there's a phase change going on. So let's add that. So anytime you see a plateau, like a flat plate, whenever you hear the word plateau, you can think of plate. A plate is flat. So whenever you see a flat line, that means there's a phase change going on. It's changing from a solid to a liquid, from a liquid to a gas, whatever the situation here. So solid starts, temperature's rising, flat. That means something's happening. It's changing. It's melting. Okay? And then anytime you see this little curve, you see a new state of matter. So this first curve is solid. Now you have a liquid. What do we have here? Another flat line. So that means a phase change is happening. So now you have a liquid and you're increasing the temperature. Temperature stays flat. When the temperature stays flat, the phase is changing. Over here we have vaporizing. And then when it starts to pick up again, you have a new state of matter, you have a gas. You can do this backwards too. Remember that. So, if you start with a gas and you go backwards to a liquid and then you end with a solid, okay, from gas to liquid, that was what we did up here, right? How do you make a gas to a liquid? This flat line is called condensation. It's condensing. So anytime there's a flat line, you got it, phase change. So these are my phase changes. And anytime you see a curve, it's a new state of matter. And then from liquid, there's a flat line, so something's happening here. It's going from a liquid to a solid. We call this freezing. And then solid. Okay, this is adding thermal energy. Okay, we're just adding a little extra. And this is over here removing thermal energy. Okay, at point A, What is the state of matter in a substance? Well, now that we have this all beautifully labeled, we can just breeze right through this. Solid. At point C, what state is it? It's a liquid. Right here. At point E, what is it? It's a gas. What states of matter is the substance between points C and D? So if you look over here, between C and D, it's a liquid. Okay. What is happening between points B and C? Okay, we already said it's melting, which means solid to liquid. What is happening between points D and E? We already labeled that as vaporizing, which we know goes from liquid to a gas. Why does the temperature stay the same between points B and C? Well, what did we say happens when it plateaus, when the temperature stays the same? There's a phase change going on. Okay, ice cube is melting, water starts to boil. So anytime you see a flat line, a plateau means a phase change is happening. What is happening to the molecules between points C and D? So here's C, it's a liquid. Temperature's increasing to D. So if temperature's increasing, what's happening to the motion of the molecules? They're speeding up and spreading farther apart. Alright, let's knock out this true or false section, and then you're going to take this study guide, you're going to study it, and you're going to do awesome on your test. True or false? If it's false, fix it. Air is a good insulator of heat. We talked about that. That is true. If you add thermal energy to liquid water, it will freeze to ice. Adding thermal energy means like it's getting hotter. So if I add thermal energy to liquid water, will it freeze to ice? No. False. Let's fix it. If I add thermal energy to liquid water, it will freeze to ice. You need to change this. It will vaporize to a gas. Boom. So that's what I mean by fixing it. So you just cross it out, right to the side. The coldest possible temperature is 0 Kelvin, but it hasn't been reached yet. That is true. 0 Kelvin, that's not okay. But 0 degrees Kelvin is called absolute zero. That's when all molecular motion stops. Heat and thermal energy mean the same thing. You should know that is false. Okay? C number 1. Okay? Number 1, remember this. Heat and thermal energy do not mean the same thing. Heat is the transfer of energy from hot to cold. So heat, transfer of energy. Thermal energy means total kinetic energy. And then temperature means average kinetic energy. All of these definitions you need to get straight for your tests. Okay? They do not all mean the same thing. Electromagnetic waves from the sun is an example of radiation. True. Vaporizing changes liquids to gases. We just answered that one. So this is true. White colored objects absorb the most heat, so they get hotter than other colors. This is false. Hopefully you remember from our wave unit that black colored objects, so we'll just cross that out and we can write black here. black colored objects, that's why you don't want to wear a black shirt on a hot day. You want to wear a white shirt because white reflects the heat, black absorbs the heat. The particles of a substance move slower when heated. Hopefully you know by now that's false. So you can say the particles of a substance move faster when heated, or you can say the particles of a substance move slower when cooled. Either way, I don't care. The boiling water rising and cooler water falling in this tea kettle is an example of conduction. So it's talking about, okay, this hot water on the bottom, this is going up, and then eventually some of that water is not going to stay cold, hot forever. Eventually the cold water is going to go down, and it's just going to make this current. It's going to keep going and going and going. So what did I say you need to remember anytime you see this? Hot air rising, cold air falling. That's an example of convection. So is an example of conduction? No, I'm not physically touching anything. I'm talking about this and what's going on inside the water. So false. This is an example of convection. Conduction would be if I were to touch this tea kettle and burn my hand. That's conduction. Okay? But this right here is referring to convection. Hot air rising, cool air falling. A medium size, like a grande coffee from Starbucks, has less thermal energy than a small size coffee. Hopefully you know by now that's false. Okay, this is bigger, so if it has more mass, they're both the same thing. They're both cups of coffee. But because this is larger, this is medium, and this is small, it's going to have more thermal energy. Warm air falls to the ground because it is more dense than cool air, which rises up. Same thing, guys. This is false. So, you can change this to cool air falls to the ground because it's more dense than warm air, which rises up. 10 milliliters of cold water will reach boiling point slower than 1,000 milliliters of cold water. Let's think about this. If I have, you know, 2 graduated cylinders, let's say this one has only a little bit, only 10 milliliters of water, and this one has pretty much the whole thing is full, 1,000 milliliters of water. Which one's going to boil first? If I put both of these on top of a stove, which one's going to boil first? This one, because there's less of it. This one's going to take more time for the heat to go through it. So 10 milliliters of cold water will reach boiling point slower than 1,000 milliliters of cold water. This is false. So we can just change this one to faster. Alright, this is your study guide. Now that you've gone over it with me, you need to go back. I would highlight important things so you can say, okay, this is going to be solid, liquid, gas. Go back and, you know, put question marks on things you still don't know. Come to class with questions, but definitely go over everything 2 or 3 more times before your test.